Hello, this is a video presentation for the 2020 IEEE International Conference on Soft Robotics. My name is Brian Johnson, and I'm a PhD student in the Advanced Medical Technologies Laboratory at the University of Colorado Boulder. And today I'm going to be presenting our research on the identification and control of a nonlinear soft actuator and sensor system. I'm going to begin by discussing the motivation for this research, which is related to HASEL actuators. And then I'll discuss how we integrated a soft strain sensor onto the actuator in order to measure its displacement. And then I'll go through the system identification techniques we used to determine the transfer function of this actuator sensor system. And finally, I'll talk about how we use this information to create a controller for real-time closed-loop control. So let's begin with our motivation. HASEL actuators, or hydraulically amplified self-healing electrostatic actuators, are a new class of soft actuator developed by the Keplinger research group. They're characterized by a high actuation frequency, good efficiency in comparison to other soft actuators like pneumatics, and the ability to be scaled down to compact sizes. In combination with compact power supply systems, these could be very useful for untethered soft robots. And in a nutshell, HASELs are made with two electrode layers with a liquid-filled dielectric pouch in between them. When voltage is applied, the electrodes zip closed and displace the liquid, causing a shape change, as you can see in the figure here. A modified form of this layout can be folded over itself to create a stacked unit, which acts as a linear actuator, as you see here. As the figure below shows, applying a voltage causes the electrodes in the middle to come together, displacing the fluid to the left and right sides, and causing this upwards expansion. This geometry is useful for soft robots, but the dynamics of these actuators are unknown, and from what we did know, they were very nonlinear. And in addition, there's this simple problem that effective closed-loop control hasn't been achieved with these actuators before. So if we want to eventually build untethered soft robots with foldable HASELs, we need to overcome these barriers, and that was the primary motivation for this research. Now let's talk about the strain sensor that we developed to measure foldable HASEL displacements. But first, let's discuss why, because HASELs do have the ability to self-sense using their own capacitance. However, this self-sensing is currently limited because it requires specialized and expensive AC circuitry to perform, and it also has a very nonlinear relationship between the HASEL capacitance and its displacement. So this motivated us to develop a simple external sensor that only requires minimal circuits and very simple techniques to use. So we developed a capacitive-based strain sensor using this design. This is a fairly standard capacitive sensor design based on a parallel plate capacitor, where stretching the sensor causes a decrease in the thickness of the dielectric material, thus causing a change in capacitance. We manufactured the sensor using EcoFlex 30 as the dielectric material, and EcoFlex 30 mixed with carbon black particles for the electrodes. We measured the capacitance of this sensor using an LMC 555 timer circuit in a monostable configuration, which is this circuit shown on the right. Its operation is fairly simple. The input is a 3.3 volt square wave with a fixed duty cycle, and the output is a 3.3 volt square wave with a variable duty cycle, where the duty cycle is proportional to the capacitance of our strain sensor. We can then use interrupts in a microcontroller to measure the elapsed time between the rising and falling edges of this output signal, thus determining the duty cycle and converting it into a scalar value of strain that we can use in our closed-loop control. We integrated our strain sensor with a folded HASEL actuator by simply wrapping it around the perimeter of the actuator, as you see here. So when the actuator expands, the sensor becomes stretched on both sides, causing that change in capacitance that we can then measure using the 555 timer and the interrupt method. With this design, however, we also had to add a dielectric shield to the top and bottom of the actuator to reduce noise, because what happens is that the electric field from the HASEL actuator couples with our sensor electrodes. By increasing the separation between the sensor electrodes and the actuator electrodes, we can keep this interference to a minimum and reduce noise in the sensor measurements. Now that we've established what our soft actuator and sensor system is, we can begin to characterize its dynamics. And we begin by applying the principle of superposition. So any input voltage signal, like this one, can be broken up into a static offset component and a dynamic sinusoidal component. We then assume that the output response of the HASEL can also be broken up into the same static and dynamic terms. If true, this allows our dynamic model of the HASEL to cover almost the entire voltage operation range using only a single transfer function. We used a chirp analysis to determine if this was actually true. Our testing inputs were high voltage sinusoids of increasing frequency, and the system output is the HASEL displacement, which we measured using a laser distance sensor. The voltage sinusoids ran from 0.001 up to 20 Hz in 20 seconds, and we tested these dynamic sinusoids at multiple static offsets from 2 kilovolts to 7 kilovolts. This input-output data can then be converted into a frequency response plot, which is seen here. This plot shows that, in general, our separation of static and dynamic responses holds true. Although the responses at each static offset have some varying DC gain, the overall shape of the frequency response is almost the same between all input signals. So using this data, we fit a single transfer function starting from a notch filter design and then using MATLAB's system identification toolbox to create a better fit. We also tested our strain sensor in step responses of the actuator. And as you can see, the sensor has minimal phase lag and is able to track the actual displacement really well when compared with the laser sensor as the ground truth. However, this test highlights one of the nonlinearities of the folded HASEL. As you can see, when the actuator is moving upwards in activation, the response is much sharper than when the actuator is moving downwards in relaxation, which is more damped. And in a second, I'll describe how we accounted for this in feedback control. Now that we have this actuator and sensor data, we can look at the problem of closed-loop control. We started with a basic PID control scheme, but with the addition of a dual-mode controller, as you can see in the block diagram here. This is our way to account for the HASEL nonlinearity that I just discussed. By separating the controllers, making them dependent on the reference error, we can separately control the activation and relaxation dynamics. So our C- controller, seen here, is a bit more aggressive in order to account for the extra damping of the relaxation response. In this block diagram also, we treated our sensor transfer function as an ideal sensor because of the good tracking shown in the step response data. And then, of course, the plant transfer function comes for the frequency response data that we just examined. Using this block diagram system, we then designed our two controllers and converted them to the discrete time domain to be implemented in our hardware. And this is what the closed loop hardware looks like. To give a brief run through, we start with the sensor, which will have some change in capacitance as the actuator expands and contracts. Then the capacitance will be measured using the 555 timer circuit that we discussed, and the output of that will be sent to our microcontroller unit, or MCU, where we use interrupts to convert this to a scalar measurement. At the MCU, here we perform control and compute a command voltage to be sent to the actuator. Meanwhile, we also send data to a computer to be stored. And the command voltage is sent as a low voltage to the amplifier and comes out of the amplifier as a high voltage signal, which is then filtered using a 500 Hz low pass filter in order to reduce noise from the amplifier. And then this filtered signal is finally applied to the HASEL actuator, causing a change in displacement, and the loop repeats at 200 Hz. And the results of this closed loop control are very promising. So we've shown, compared to the open loop, a factor of 10 decrease in the activation rise time and the relaxation rise time saw a decrease by about a factor of 2. Although the theoretical steady-state error should be 0 due to our integrator and the controls, it only remained within 5% due to noise of the sensor. Here's what the closed loop feedback looks like in real time. So the top signal you see here is our strain sensor measurement compared to the reference displacement, and the bottom signal is the ground truth laser sensor measurement. So you can see that even with a load applied, the actuator is able to easily and quickly track the reference command. Now, the next steps for this research is to first improve the sensor measurement by reducing noise, and this could be done with a Kalman filter, or it could also be done by improving the shielding technique around the HASEL to reduce the coupling effect that was seen there. Another thing that we hope to do is to make our plant model more accurate by incorporating the multiple DC offsets that we saw in the frequency response data. So this could be some kind of adjustable gain plant. This would make our transfer function more accurate across the entire operating range of the actuator. And then finally, we'd like to characterize the dynamics of untethered power supplies so that we can create small-scale untethered closed-loop control of a HASEL system for soft robots. And now I'd like to mention the references used in this presentation, as well as acknowledge the research labs we collaborated with, as well as our funding sources. So that concludes our video presentation. I hope you enjoyed it. If you have any questions, feel free to contact me at the email address below. And with that, thank you for watching, and I hope you're all staying safe and healthy during these difficult times. Thank you.